Hello everyone, I am Tanmay Sinha and I will be presenting our work Multi-Teacher Curriculum Design for Sparse Reward Environments. The work was done by Chaitanya Kharayal and myself under the supervision of Matthew Taylor. Here I provide an overview for our method. First, we propose a technique that we call adversarial multi-teacher curriculum design with traces, which we introduce to combat the problem of learning in sparse reward environments. The technique involves multiple teachers engaged in a game against the goal conditioned student. Our main contributions include introducing simultaneous multiple teacher training and showing that it outperforms existing baselines. We also introduce a novel sparse reward driving simulator environment that we believe will be a good environment for future research in this area. We also analyze the effect of the behavioral cloning loss on both the teacher and student agents and provide empirical results suggesting the promise of our method. The initial motivation for introducing our method was the problem of learning in sparse reward environments. Such environments are abundant in the real world, and RL agents often face difficulty in such environments. The reason is that the agent can take a very long time before stumbling upon a rare positive outcome without any guidance. This sparse feedback from the environment results in weaker gradient updates. There are many traditional methods to deal with such environments, such as reshaping the reward function or rewarding the exploratory behavior based on other metrics such as information theoretic metrics or learning an intrinsic reward function, etc. Yet these fail to generalize well. Another promising class of methods for learning in these environments is curriculum-based methods, where the agent learns under a set curriculum. This curriculum can be designed either by humans, which is impractical, or we can use a heuristic-based teacher agent to set up the curriculum. Yet these fail to still generalize well on all environments. Building on the prior work of adversarially motivated intrinsic goals and taking inspiration from other adversarial techniques such as GANs, we introduce a novel approach to learning in sparse reward environments. Our technique involves a teacher and a student engaged in a two-player game. The teacher agent is rewarded based on its ability to set goals in a curriculum style, and the student is a goal-conditioned agent, which is rewarded based on its ability to reach those goals. However, in our experiments, we observed that a single teacher does not generate a diverse enough curriculum, and while the student is able to reach all the goals set by the teacher, it is not able to generalize well on unseen goals. Thus, we introduce the notion of allowing multiple teachers to simultaneously train a single student. This transforms the original two-player game into a multiplayer game. We observe that it provides two benefits. First, it speeds up the training process while also increasing the generalizability. The following figure represents one teacher-student rollout. In each teacher-student rollout, we sample a state S0. This is used as the initial state. Starting from the initial state S0, the teacher interacts with the environment for a fixed number of time steps to reach the goal state G. This state is used as the goal while teaching the student. Again, starting from the initial state S0, the student now interacts with the environment and tries to achieve the goal G. If it is able to reach the goal, then the teacher is punished and the student is rewarded. Whereas if it is not able to reach the goal, then the teacher is rewarded and the student is punished. Note that the policy for the student is conditioned on the goal generated by the teacher. This teacher-student rollout is carried out for each of the teachers in a single episode. The teacher-student setup outlined above has two major advantages. First, we know that the goal G generated by the teacher is reachable starting from the initial state sampled. Secondly, and more importantly, the teacher provides a valid trajectory from the initial state S0 to G. This trajectory can be used to guide the student while teaching through the use of something called behavioral cloning. In addition to the standard RL loss, we add a behavioral cloning loss to the student's objective, which is as follows. As discussed earlier, if the student is able to reach the goal, the teacher gets a -5 reward and the student gets a +5 reward. Otherwise, if the student fails to reach the goal, the teacher gets +5 reward and the student gets 0 reward. Note that these are sparse rewards and are only provided at the end of each rollout to both the student and the teacher. Ideally, the teacher should aim to generate increasingly difficult goals which form an ideal curriculum for the student. The algorithm is provided on the right hand side. Due to the unavailability of popular sparse reward environments for curriculum learning, we have created a driving environment to test our algorithms and other baselines on. We believe that this environment will be a good test bed for future research in this area. The code is fully open source and is available at the given link. Next, we move on to the experimental results. The following graph shows the success rate on unseen goals versus episodes, averaged over multiple runs for different teachers. We compare the performance of our method against the no curriculum baseline, which is a standard TD3 agent trained on random goals. Note that it performs comparably to a random agent due to receiving insufficient feedback from the environment. Secondly, note that with the increasing number of teachers, two things improve. First, the rate of learning increases, and secondly, the peak generalizability also increases. Note that to make a fair comparison, we have made sure that each algorithm sees an equal number of goals in each episode. The following graph demonstrates the effect of behavioral cloning on generalizability. The student trained against the no BCL single teacher does not perform as well as the agent trained with a single teacher with behavioral cloning. This is because without behavioral cloning, the student is unable to reach the goals set by the teacher. The following graphs demonstrate the correlation between the student's adversarial reward, that is, the reward that it gets by beating the teacher, and the success rate on unseen goals. For a student trained against multiple teachers, it is observed that there is a strong correlation between the adversarial rewards and the generalization, whereas this is not the case for a student trained against a single teacher. This shows that with multiple teachers, a diverse curriculum is generated, which helps in the generalizability. We carried out some of our experiments using the Cogment framework. In our experience, the modularity that Cogment was provides enabled us to easily and quickly modify it according to our needs for fast experimentation. We would like to continue working on Cogment and contribute to its open source community, as we believe that it's a promising tool for future research in this area. The code for the Cogmentverse implementation is available at the given link. Thank you.